Hello, and welcome to this vectors subject extension. It's not 2D and 3D vectors, it is only 3D vectors, but we will look at a geometric problem and we'll look at a forces problem to see how we can apply our vectors knowledge. We have here, this first question, a diagram that shows a tetrahedron, OABC. We've got lowercase vectors, A, B, and C, which are the position vectors of A, B, and C, respectively. And then we're told that these points P, Q, R, S, T, and U are midpoints. All right, so, getting through all the language here, when we look at P, Q, R, S, T, and U, we just have to remember that they are halfway along the lines that they're on. So then we're asked to prove that the line segments PQ, RS, and TU meet at a point and they bisect each other. So it's this point right in the middle of the diagram. So whenever we're asked to prove that the line segments bisect each other, we focus on those line segments. So the first one I'm going to focus on is PQ, the vector PQ, this one here. And what I want to do is to write PQ in terms of A, B, and C, because then I'll be able to do some work on that and I'll be able to prove that it bisects one of the other lines. So describe the vector PQ. We're going to go from P to O. We're going to then add O to A. So we're trying to journey from P to Q along vectors that we know, plus AQ. Okay. So the journey from P to O, you can see here, is given by minus a half of OA. All right. It's traveling opposite, OC. It's traveling opposite the direction of that vector, so it's going to be minus, and it's half because P is the midpoint of OC. So then we're going to go along OA, and then we're going to go from A to Q. Now A to Q is 1/2 of AB. So that's going to allow us to write things in terms of our lowercase a, b, and c. Minus a half of OC is minus 1/2 of C, plus OA is plus A, and then AB, so half of AB. Now, if we think about AB, we're going to have to think, how do you get from A to B? Well, you travel backwards along A and forwards along B. So we have plus half B minus A. So there we've written the journey from P to Q in terms of A's, B's, and C's. And I'm just going to tidy it up and write them. How many A's, how many B's, and how many C's do we have? Well, we've got A plus minus a half A, so we have half A. We're going to have plus half B. And we've got this minus half C. So that's our journey from P to Q in terms of our A's, B's, and C's. The next thing we're going to do is the same thing for RS and TU. So we'll go from R to S. First of all, write it out using its capitals. I could go this way, so left round the shape. So I can go from R to O, plus O to C, plus C to S. Okay. R to O, O to C, C to S. So R to O is minus 1/2 of OA, right, backwards along A, and it's half because R is a midpoint, plus OC, plus from C to S, which is 1/2 of CB. Let's write that in terms of our little A's, B's, and C's. We've got minus 1/2 A plus C, and then CB, if we look at CB, how do we get from C to B? Backwards along C, forwards along B. So we're going to have plus half of B minus C. Okay. Expand and collect, minus half A plus C plus minus a half C. So we've got plus half C. Let's write them as A's, B's, and C's in order. So how many B's? Plus half B. And then plus the half C, so C plus half times minus 1, so minus half C. So we've got PQ and RS. Let's do exactly the same thing then for TU. Again, we have to do this for each of our line segments in which we're interested. So T to u, we're going to go from t to o, okay, backwards t to o, plus o to a, plus a to u. So tu is minus 1/2 of OB, all right, backwards along B, and it's a midpoint of OB because we're told that in the question, plus OA, plus A to U is 1/2 of A to C, and we can write it in terms of A's, B's, and C's now. So we've got minus 1/2 B plus A plus 1/2, and then from A to C, that vector A to C is just minus A plus C, or C minus A. And we'll do exactly the same things we did before. A plus minus 1/2 A is 1/2 A. We've got our minus 1/2 B, and then we've got plus 1/2 C. So there are our three line segments, PQ, RS, and TU, written entirely in terms of A's, B's, and C's. Now we need to get to the point where we start thinking about where do these lines intersect, all right? Because they do on a diagram, but we need to think about where they intersect. So I'm going to say let X be the point of intersection, all right? Now what I want to do is I want to write a way of getting from Px, from R to X, and from T to X, all right? So X is our intersection. How do we get from P to X then? Well, from P to X, right, in the middle here, I'm going to go from P to O. Then I'm going to go from O to R. Then I'm going to go from R to X. All right. What does that look like? P to O is minus 1/2 C. Okay, so I can go straight to that bit. O to R is 1/2 A. And from R to X is the interesting bit. Because from R to X, we're traveling a fraction of the way along R to S. But we don't know what that fraction is. We're hoping it's 1/2, but we don't know that it's 1/2. So I'm going to leave it as an unknown. And I'm going to write it as R, okay, an unknown R, because we're starting at R. So it's R multiplied by RS, all right? So just leave that as capital letters for now to emphasize. Okay, so minus C plus A, minus 1/2 C plus 1/2 A, plus a fraction of RS, and the fraction is represented by this unknown R. So let's just write that. So we've got minus 1/2 C plus 1/2 A plus R multiplied by RS. Now RS is this one here. We've got minus 1/2 A plus 1/2 B plus 1/2 C. Let's collect our like terms together. So how many A's do we have? We've got 1/2 plus minus 1/2 R. Lots of A. Okay, so we've got 1/2 minus 1/2 R A. How many B's do we have? The only B is plus 1/2 RB. So R over 2 B. And then with C's, we've got R over 2 minus 1/2. So we've got plus R over 2 minus 1/2 C. Okay, so that's my journey from P to X. And that's going along the vector RS. All right. I want to now describe P to X in a different way. And I'm going to describe it as the journey from P to X. But this time, I'm going to use a different vector. All right. I'm just going to use the vector PQ. And I can say that by saying that it is a fraction, and I'll call it S just as a number, of PQ. All right. So I've written P to X using RS. This time I'm going to write P to X just as a fraction of the vector PQ. Okay? Two different ways of writing the same vector. So that's going to be S multiplied by 1/2 A plus half B minus half C. Okay, I can expand that. I can just say S over 2A plus S over 2B minus S over 2C. So what I've got now is two different ways of getting to the same point from the same point. One of them goes through the vector Rx that we wrote down at the start, and the other one goes through the vector PQ. Now it's really important that we're doing the same vector P to X, because we're going to equate these two. So therefore, S over 2A plus S over 2B minus S over 2C is equal to 1/2 minus R over 2A from this line plus R over 2B plus R over 2 minus 1/2 C. And what I need to do is to equate all of our A's, B's, and C's. Now, the thing that they've all got in common at the minute is a half, so I can ignore the half at this point, all right? So just to simplify things, I'm going to multiply everything by 2. So I've got SA plus SB minus SC equals 1 minus RA plus RB plus R minus 1C. Okay, so that's just, we're allowed to do that. It doesn't matter that it's a half. We're simplifying now to equate things down. So now I need to know how many A's are on the left, how many B's are on the left, how many C's are on the left, and equate that with the number of A's on the right, B's on the right, and C's on the right. So let's do that. So this S, so I'm going to equate my A's first. S equals 1 minus R. S, it has to be the same as 1 minus R. If I equate my B's, S equals R. And then if I equate my C's, minus S equals R minus 1. Okay, so just equating those C's. Because they're the same vector, they have to be the same. So let's start by looking at this. S equals R. I can substitute S equals R into here. So since S equals R, R equals 1 minus R, which means 2R equals 1, which means that R is a half. Now, as S equals R, that means that S also equals a half. And we can double check this with C. So if S equals R minus S equals R minus 1, then S equals 1 minus R, which is exactly the same relationship as A. And so we've got the fact that R is a half and S is a half. Now what does that mean? Well, that means that the journey from P to X is 1/2 of the journey from P to Q. So therefore, Px equals half PQ. And it also means that Rx is half Rs. And all of that because, if we look back at our two equations here, so we've gone from P to X by minus 1/2 C plus half A, and then a fraction of the vector we're interested in. So the fraction of Rx is R, and R turned out to be a half, so it's along half of Rx. So then, half of Rx, half of Rs, half of Rs. And if we look at Px, well, we knew we were going a fraction of the way along PQ, and the fraction of the way along PQ was a half. So that's it for, we've proved that PQ and RS bisect. Okay, that's what we've proven. Now we need to go a little bit further because we've proved that 2 lines bisect. We need to prove that the 3 lines bisect. So we're going to have to bring in TU into So I'm going to start with Px again, because we need two equations to equate to each other. So Px is going to be, I'll use another variable, t. Actually, do you know what? We know that Px is r times Pq, okay, which is going to be r multiplied by our Pq vector. Our Pq vector is half a plus half b minus half c. And we also know that Px, this time we want to describe the journey from P to X, but using the vector t to u, because we want to know if it's halfway along t to u. So if we think about it, from t to u, we need to go minus a half c plus a half b plus tu. So we're going to have minus half b, sorry, minus half c plus half b plus some distance along tu, which I'll indicate by this fraction t right here. Okay. So that's going to be minus half c plus half b plus t multiplied by my tu vector, which was half a minus half b plus half c. Just double check I've written that down right. Oh, minus the b plus the c. Always worth checking, isn't it? A lot of working to keep track of here. Which is, let's see, how many a's do we have? We've got t over 2a. T over 2a. How many b's do we have? We've got half minus half t. So we've got 1 minus t over 2 lots of b. And then we've got how many c's? Minus a half plus a half t. So we've got 2 over 2 minus 1 lots of t. So that's half. Okay, so now we have our vector px in terms of tu. And we're going to let this be the same as here. Right? So we've got r over 2a plus, just to simplify, r over 2b minus r over 2c. And now we make these two equal to one another. Right? Because the vector from P to X has to be the same no matter which way we've gone. So we'll say r over 2a plus r over 2b minus r over 2c equals t over 2a plus half minus t over 2b plus t over 2 minus 1/2 c. Again, we'll multiply everything by 2 to get rid of all these halves. We get RA plus RB minus RC equals TA plus 1 minus TB plus T minus 1C. How many A's do we have? Equate again. So we equate A, R equals T, we equate B, R equals 1 minus T, and we equate C, minus R equals T minus 1. So using R equals T, T equals 1 minus T, so T comes out as a half in the same way as before, which means that R is also a half, and if we do this one, we just verify that. So if R is a half and T is a half, then that means that we have gone along 1/2 of TU. Okay. So since R is a half here and T is a half, then the two vectors we're interested in, PQ and T, I forgot what I'm doing here, PQ and TU bisect each other. And by proving that PQ and TU bisect and that PQ and RS bisect, we've proven that all three bisect. So the general theme of this question really is, when you have line segments like this and you're asked to prove that they bisect or that they intersect or that they intersect in a ratio, begin by writing the vector PQ, the vector RS, the vector TU. Once you have those, you can start to put together vector equations. Now, what you're looking to do is do the same journey from, say, for example, in this case, it was P to X. And you want to go two different ways. One way, using one of your three vectors, and the other way, using another of the three vectors. And when you do that, you then equate them, remembering that you've got this kind of unknown. How far along this line does it go? We don't know. How far along this line does it go? We don't know. And what we're trying to do is to show that these two don't knows, S and R in this example, are the same. All right? And when we show that they're half, then they bisect. And then we had to do this additional bit because we had three lines bisecting, so we had to repeat the process using the third line that we didn't use at the beginning. So quite a lot of work in to kind of keep track of. I will post my answers in the chat as well, so you'll see the PDF of this working, so you can pick through it, because it's quite a lot to follow. All right, and the second quicker example that we're going to look at is just when we use 3D vectors in mechanics. So we'll look at, forces. We can use it in kinematics. But let's have a look at this question. We've got a particle of mass 6 kilograms acted on by two forces, F1 and F2. Then we're told the vector of F1, and we're told that the acceleration of the particle is this. Then we have to find F2. Now the key thing here that we're going to work on is Newton's second law, F equals ma. How do I know it's F equals ma? We're given the mass, all right? If you're given the mass and you're talking about things like acceleration, you need to bring in Newton's second law, all right? And to do this question properly, we just remember that F represents the resultant force, not just any old force, all right? So the resultant force, in our case, is the sum of the two forces, F1 and F2. So F1 plus F2, that's our resultant force, equals mass times acceleration, which is going to be 6 multiplied by the acceleration. I'm going to write this as a column vector rather than i's, j's, and k's. But we've got 2, 0, minus 1. Remember, just because there's no j written in the question doesn't mean that we just miss it out. We have to include it as 0 j's. All right, so I'm just writing that as a column vector because I prefer to work with column vectors. So let's put in some more information that we know. F1 is 7, 3, and 1, plus this F2 is 6, 2, 0, minus 1. How do we work out what F2 is? We subtract F1 from both sides, and at the same time I'm going to multiply by this 6. So I have 12, 0, minus 6. Okay, 6 times this, 6 times this, 6 times this. And then I'm subtracting 7, 3, 1. And so my F2 comes out as 12 minus 7, 5, 0 minus 3, minus 3, minus 6, minus 1, minus 7. And the question asked us to use I, J, and K notation, so that's what I have to do. So I have 5, I, minus 3, J, minus 7, K. So, again, things to look out for when you enter this sort of question. If you're talking about forces, and particularly when you're given a mass, chances are you need to use F equals ma, and you just then apply your vector algebra to that question. You may be asked a SUVAT question. Similarly, you just use SUVAT, but you use vectors instead of whole numbers. So I'm going to finish that there and post this video up in the general chat. I've also got a couple of questions I'll throw in there in case you want to try them, and I'll post the answers to those a little bit later on. Thank you.